Thank you, Mr. Chairman. The title of my talk is Challenge Project Overview. If we look at the properties of the main semiconductor used for power devices, we can see that both silicon carbide and gallium nitride have a breakdown field much higher than silicon. This gives the opportunity to realize a power device with a low power dissipation using these materials. Furthermore, silicon carbide has a high thermal conductivity, and then it is possible to realize power devices that can manage very high current without a large increase of the temperature of the device. If we compare 3C silicon carbide and 4H silicon carbide, we can observe that 3C silicon carbide has a lower band gap and higher electron mobility. This property of 3C silicon carbide can be very interesting for several applications. In fact, if we plot the on resistance of a MOSFET versus the breakdown voltage, we can observe that 3C silicon carbide has a very low on resistance in the range between 100 and 1200 volt. This range of breakdown voltage is extremely interesting because there is a large market between the typical silicon market and the 4H silicon carbide market. In this region, the main application will be the electrical vehicles, that is one of the market section that is predicted to grow more in the next years. Actually, it's not possible to grow a bulk wafer of 3C silicon carbide, and this material is typically grown on a silicon substrate. This fact gives the advantage that large wafers can be directly obtained using the large silicon wafers up to 12 inches in diameter. The main problem of this technology is the large difference in the lattice constant between the two materials that produce high density of defects at the interface. It is also present a large difference in the thermal expansion coefficient that produce a large stress during the cooling after the growth. This difference produces also some effects on the device and on the wafers. In fact, the high density of defects produce a high leakage current of the junction. Instead, the thermal stress and the presence of defect at the interface produce a large bow of the wafers. In this project, we want to solve the main problems that delay the development of the 3C silicon carbide power devices, reduce the crystallographic defects and the strain. Two main directions will be followed in this project: the use of compliant substrates to try to decrease both the strain and the defects density, and the realization of a ball that avoid all the problems connected to the hetero-epitaxy process. We call compliant substrate some special substrate with some structure that can reduce the defects and the stress in the final material. One of these substrates is the inverted silicon paramid substrate. In this case, several parameters are realized in the silicon substrate to improve the reduction of stacking faults at the 3C silicon carbide silicon interface. Another compliant substrate use the 3D grow on pillars to reduce both defects and stress. In fact, in this structure, the stacking faults can be stopped by the sidewalls. Furthermore, this structure can also reduce the stress through a bending of the pillars. Another important approach used in the project is the development of a bulk technology. Using different approaches can be obtained large wafers of 3C silicon carbide that can be used for the realization of power devices. This material has different crystallographic defects, stacking false antiphase boundaries, point defects, but has been observed that increasing the thickness or decreasing the growth temperature, it is possible to improve the quality of the material. During this project, it has been performed a lot of fundamental work on the behavior of the main defects of the material. It has been observed that the antiphase boundaries produce a high leakage of the junction. For this reason, several approaches have been used to eliminate these defects. Even the stacking faults produce a larger leakage of the junction as observed by contact IFM measurements. Then different approaches have been used to reduce as much as possible this defect. Several simulation tools have been developed inside the project. One of the most interesting tools is a new Monte Carlo code that gives the possibility to simulate the evolution of defects inside the 3C silicon carbide during the growth. On the left, we can see a result of this simulation code where the evolution of an antiphase boundary is reported. On the right side, instead, the quantum transport of the main defects in 3C silicon carbide has been simulated. Using these tools, it is possible also to simulate the interaction of different defects. Another important aspect covered by the simulation is the understanding and the optimization of the 3D growth on pillars. On the top of this slide, it has been studied experimentally the evolution of a 3D growth on pillars and all the growth parameters. The growth rate on the different phases has been introduced in the model. All this information has been used to simulate the merging of 3D growth on pillars using different mask designs, and this simulation has been compared with the prediction of the simulation. The agreement is really good in this case. Finally, also some MOSFET simulations have been performed to understand which difference can be expected in the electrical characteristics with respect to 4H silicon carbide for the same device geometry. From this simulation, we observed an increase of the forward current and a reduction of the breakdown voltage. Several PN junctions have been realized in this project, and while they forward bias EV characteristics are quite ideal, in reverse bias a high leakage current is observed until now, and we are trying to reduce the defects to reduce essentially this leakage current. It is the major problem at the moment. Thank you for the attention.